So we should continue on with our study of logs and exponentials, right?
I have a question about number 9.
Uh-huh.
So, I used to rational root them, and I didn't get anything right. They all came back negative. They were all bad numbers.
Let's see, have I posted the solution to test 3 yet? Problem 9 you asked about? Let's see here. So P of x cubed minus 7x squared plus 7x plus 15. I said factor P of x completely, right? So, so 15 suggests plus or minus 1, plus or minus 3, plus or minus 5, or plus or minus 15 as possible roots, because the leading coefficient is 1, right? So we don't have to worry about fractions. So I usually start with the easiest one, 1. Well, that's 1 minus 7 plus 7 plus 15, which is 23 minus, I think that's 16. Is that right? Let's see here, 22, 23, 23 minus 7, 16, yeah. Anyway, the point is, whatever it is, it's not equal to 0, all right? P of minus 1 is minus 1 minus 7 plus 15, which is equal to 0. So if you didn't get that was equal to 0, you missed a sign or something. Yeah. Now, so of course this says that x plus 1 is factor, right? Now, try plugging in 3. Let's see what happens there. That's 27 minus 7 times 3 squared is 9, plus 7 times 3, which is 21, of course, plus 15. So what we're looking at is 27 plus 21, which is 48. 48 plus 15, 58, 63. So 63 minus 7 times 9. So 7 times 9 is 63, right? So that's 0. So that tells us that x minus 3 is factor, right? And at that point, we could be sneakier. We could go, okay, well, well, you got it. Thanks. So yeah, it's 0. And so if you think about it, if P of x, like think about this, if P of x is equal to x plus 1 times x minus 3 times something, what does that something have to be? Notice that, this is not, this is something that needs to be said. I graded test 3, and I saw a lot of people, they factored, like you factored a quartic, a fourth order polynomial, right? And I had some people give me back like just x plus 1 or something. That's crazy. I mean, this is not good. If we have a factoring of a polynomial, it should have the same degree. It's not hard to see degree. Like if you say something fourth order is equal to something first order, that doesn't work. right? You should be able to think about multiplying it out and getting back that x to the fourth. I had another person factor the fourth order problem and it have 5 factors. But if it's a fourth order polynomial, you can't have 5 linear factors. That would make it fifth order. So like, I think people, something easy we could all do, like a lot of you, not everybody, but about half the class, check your answer in terms of, does my factoring match what I'm supposedly, factoring? Like, in other words, is the degree of my factorization matching the given degree of the polynomial? That would be a safeguard that would help you to understand if you're like really far off and need to think about the problem more, right? Now for this problem, if you didn't get them 0, right, then that either means my problem's wrong or you made an arithmetic mistake, right? So you got to like revisit them and work and try it again, like maybe calculate it backwards or something, right? Like instead of whatever you did, try to do it like a slightly different way to try to avoid making the same mistake would be my advice. What that is precisely for a given student, I don't know, but this is third order, right? So either it has one linear factor and an irreducible quadratic, right? Like in other words, the solutions are complex. That could happen. Or there should be 3 rational roots. In this case, there actually are 3 rational roots. They're 1, or -1, they're 3. And notice, I picked up another marker to have a different color. I picked up another black one. Stupid. So x cubed, right? That means when I multiply this out, I should get back that x cubed, right? So there has to be like an x here. And then, well, what else? Also, when I think in your mind's eye about like multiplying this factorization out, right? How do you get a constant term? Right, it has to be, but my point is that it has to come from multiplying the constants, right? It does not involve multiplication of the x term, right? It ends up being this times whatever we need to put over here. So if this is 1 and this is -3 and we're trying to get to 15, that forces me to put -5 here.
Yeah, I checked -5, it gave me a different,
Well, I'm sorry, I don't know what to tell you. But this one, it shouldn't be -5, it should be p of 5 that's 0. Remember, because if x minus 5 is the factor, then the 0 is the like 5, and we could check that. That's, again, this is not even needed because like I've logically deduced that this is the answer, right? But we can double check our answer by seeing if p of 5 is 0. And when I plug in 5, I get 5 cubed. So, and if I had to characterize how people got this problem wrong, it was just through exactly what you're talking about, like just a miscalculation, And I did the same, I think, in my first solution. Like, I was like, what? And then it didn't work. I'm like, something's wrong here. And I think for me, I had changed like a 3 to a 27 or vice versa. Like, I didn't really cube the 3, or I tricked myself into thinking, I don't know, it just takes one arithmetic mistake, right? And it all falls down. You have to be really careful in the calculation of in the evaluation of the polynomial. But that is 125. That's 7 times 25. 7 times 25 is 175. So minus 175. 5 times 7 is 35. 15, right? So this last 2 terms is 50. That's 50 plus 125 is 175. 175 minus 175 is 0, So, yeah. So, again, I'm sorry it didn't work out, but, So, next class, we'll go back to test 1 and test 2 and also test 3. We'll just talk about, like, how to, we'll review all the test solutions next class. So, with the time that remains here, I'm going to hopefully wrap up our discussion of logs and exponentials. There is final exam part 1, which is next week. And then, yeah, next week. And then there's also final exam part 2, which is during the final exam period, whenever that was, December, I don't remember, 7th, 8th, somewhere. It's on the course planner. I don't remember right offhand. But, yeah, there'll be Zoom. There should be a couple Zoom meetings after break, probably.
So the test on Tuesday is on these?
No. On what are those? It's on tests 1, 2, and 3, but not what I'm about to just talk about. So like the logs and exponentials, chapter 4, that is on final exam part 2, and also the homework, which I'm about to give you, but I haven't given yet. In fact, I'm going to delay giving the homework until final exam part 1 is done, because there's no point in distracting you guys from final exam part 1. Actually, I was thinking about it. So, but I should have the homework. I should have mission, like, what is it, 5, 4? I've lost track. Anyway, the final mission, right, mission 5, which will be on chapter 4, that I should certainly have for you by next Thursday, right? Maybe even by Wednesday next week. And so then the Thursday before Thanksgiving is a chance for us to come and talk about how to solve those problems together, right? And I mean, I'm not entirely sure I'm even going to have lecture, like a Zoom lecture after break. I think we're going to finish the material right now, right here. So, yeah. Oh man, it was so pristine. And then I did that. I'm not sure what they did to clean it, but I'm not sure I can get back to it. All right, so properties of logs. Let's review. Log base A of xy is log base A of x plus log base A of y. Log base A of x over y is log base A of x minus log base A of y. Log base A of x to the power p is p times log base A of x. So those are your laws of logarithms, right? And is there a question? Oh, okay. And we also have the relation with the exponential, right? Like a to the log base A of y is equal to y again. And log base A of a to the x is equal to x again, right? So those are helpful. And then, of course, we also have the natural log of, e to the x is x, and e to the natural log of y is equal to y again. Now, those are some commonly used, another commonly used facts, like log base A of 1 is 0, log base A of A is 1. I mean, we could go on with this list, right? But these are some important, often useful properties of the log. Now, I started solving some log equations for us like last time, I think. But I'm actually going to take a step back and basically go to section 4.4, I think, and work on some like simplifying expressions involving logs, right? Because that's something we should do. personally, I find solving equations involving logarithms more satisfying. Like to me, solving an equation feels like a more complete problem than just simplifying an expression, partly because the simplification of expressions problems also have a certain ambiguity. Before I do that, though, I also spent about, 20 minutes of class last time talking about like functions which are defined with a formula. Maybe not last class, but when we last talked about this stuff. Talked about functions that are defined by a formula involving a logarithm, right? And we saw that brought us back to the questions of like nonlinear inequalities, right? So when I write these expressions, there's strings attached, right? Like, for example, log base a of xy is equal to log base a of x plus log base a of y. What has to be true about x and y for me to even write that? What is an assumption of that identity? Can x or y be negative? I mean, they cannot, right? I mean, the log of a negative number is not defined for us. So in these expressions up here, I used an x in this one and that one on purpose because it's true for any x. Like natural log of e to the x is x, log base a of a to the x is x. This is true for all x, for all real x. In contrast, a to the log base a of y equals to y, and e to the natural log of y equals to y, that's only true for positive y. This is for y greater than 0. That's an assumption there. All right? So that's something we should always be looking for. We cannot take the log of a negative number. All right? So this, I'm going to work on some problems from section 4.4. Let's see here. Let's work on number 12. So here we're supposed to calculate log base 3 of 135 minus the log base 3 of 45. We'll do that one. Let's look at number 16. Here we're supposed to calculate log base 5 of 1 over the square root of 125. That's number 16. We'll do number 22 as well. Number 22, we're supposed to calculate the natural log of the natural log of e to the 200. Let's see here. And I'll also do 21 while we're at it, which is the log of 10 to the 10,000. And so for all of these, the question is to simplify them, all right? And I would add, simplify these without a calculator, all right? So we without a calculator, we want to simplify these. So what do I do for the first one? Yeah, log base 3 of 135 over 45. What is 135 over 45? He just said, it's 3. Yeah, this is 3. Let me give different instructions. Calculate this without using the log button on your calculator. How about that? You know, what is log base 3 of 3? 1, right. So I worked this problem yesterday in the other section of pre-calculus, and I gotta say, this is like really striking to me. Like, does this look like 1 to you? I mean, it's 1. I don't know. It's a kind of silly problem, but anyway, there you go. So the reason we use logs is it's a little bit lost in this day and age, right? Because we have calculators that can calculate really big numbers, right? But in my parents' generation, calculators were like super expensive, and before then they didn't have them. So we used to have to do these kind of scientific calculations using much more using logs, and we had these things called slide rules. You could actually sort of mechanically calculate logarithms using something called a slide rule. And even now, we still use logs in many applications. Like you guys, maybe if you bought a pair of headphones or something, you look for maybe like the response in dBs or something, decibels. You guys seen decibel ratings on things? No? Yes. Don't pay attention, yeah. I mean, decibel is a log scale, all right? So logarithmic scales are useful when you're looking at data which has a span across many orders of magnitude. We also look at light in terms of intensity of light. It's often looked at in some sort of log scale. We may not know this or not, but like interior light compared to like exterior light outside on like a sunny day is something like 10,000 times brighter than the light inside. But that's not our perception, right? Like, do you feel like, oh, I go outside, the light is 10,000 times brighter? That's not our experience, right? Like, it just seems like maybe it's twice as bright or something, right? I don't know. But anyway, logs are useful for log scales. All right, anyway, getting back to this. So, how do we do this one? First of all, I can pull a minus out. Like that, right? Maybe that's a good step. How can you pull a square root out of a log? Did you know? I mean, here's something, fun fact. Log of the square root of stuff equals 1/2 log of stuff. So there you go. There's another property of logs, because the square root is the 1/2 power, right? So by the power property of logs, I can pull a half out, for square root is the half power, right? So I could rewrite this as like minus 1/2 log base 5 of 125. And can you tell me what 125 is as a power of 5? 3? Did you say 3? It's 5 cubed, right? Yeah. So that's minus 1/2 log base 5 of 5 cubed. What's log base 5 of 5 cubed? Well, remember the log and the exponential are inverse functions, so that just gives me back 3 again. The log and the log base 5 and the exponential base 5, those they cancel. We just get 3 times the minus 1/2, so minus 3/2 is the answer for this one. Now, do you have to do it this way? I mean, certainly not. What's an alternative way you could have done this one? So I'll make a comment over here. What's 1 over the square root of 125? This is 125 to the minus 1/2 power, right?
Yeah.
Which is 5 cubed to the minus 1/2 power, which is 5 to the minus 3/2 power. So log base 5 of 1 over the square root of 125 is log base 5 of 5 to the minus 3/2 power, which is minus 3/2. You have a choice to make. You can do a simplification using the laws of logarithm, or you could make a simplification using laws of exponents. Either way, we should get to the same answer. I mean, this is a freedom you have and you can exercise. if you're more comfortable thinking in that way, then you can do that, you know? Sometimes you can do that, not always. Like, that's not really going to help you much here. So here I think it's helpful to look at e to the 200 as like something. So this is, you know, we have natural log of e to the box is what? Well, the natural log and the exponential, they cancel in that sense. So this is just natural log of whatever's in the box. And then what's the natural log of e to the 200? Well, again, the natural log and the exponential are inverse functions. So the natural log and the e cancel, and we get 200. If you want to see a way to make that problem really, really more complicated, watch yesterday's lecture from the other section. I found a way to make this complicated. I don't even know what happened. I'm not going to get into it here. How about this one? The logs cancel out and it's 10,000. Well, that would be part of it. Log of 10,000, right? I mean, the first log and the 10 cancel. What's the common, this is also called the common log, right? Your book calls it common log. Log base 10 is common log. 10 to the 4? So you're saying, is it 4? The answer is yes, but the reason for that is that 10,000 is 10 to the 4, right? And so that gives us 4, right? Mm-hmm. I always have this problem. Students want to give me the answer, but I want to show steps. That's good. All right, let's move on to more symbolic problems from section 4.4. We'll start out with a relatively easy one. Number 30. I like 30. Here we're looking at the natural log of the square root of AB. See if you can simplify that one. Then we'll look at 36, which is the log base 2 of s to the power 5 divided by 7 times t squared. Then I will look at number 42 maybe. That's common log or log of the cube root of x squared plus 4. And then I'll do, well, I'll do another one after that, but I'm going to wait until I can, I'll erase and put it over there. Okay, so first of all, natural log of the square root of AB. What do you think? Log to the 1, yeah, okay, yeah, fair enough. You're saying that's really AB to the 1/2 power, so I can pull the half out? Well, I still have log of AB, so I could say that's 1/2 natural log of A plus natural log of B. So the instructions to these problems say, like, expand the logarithm into a sum of logs if possible, all right? So those are the two kind of things we can do with logarithms is we can either take a sum, like a bunch of them added together and subtracted, and collapse them into a single log, or we can take a logarithm of a single expression and expand it. Those are the sort of two directions that you can go. At the moment, we're expanding, all right? I'll try to do an example with collapsing once we're done with this. That's the answer, yeah. Well, these are, so we're simplifying expressions, so the answer is going to be an expression. Like I said, it doesn't give me a lot of joy because of the ambiguity, like the sense that you have right now. Like, that's it? Are we done? Right, yeah. So this one, we do log base 2 of s to the power 5 minus log base 2 of 7t squared. Well, let me say it. Minus log base 2 of 7 minus log base 2 of t squared. So let's go ahead and do like that. So I add products on the top, and then I subtract on the bottom because it's division, and that's the law, the logarithm law. 7, yeah. Now we can do a little bit more, right? We can simplify these further by the power property of the logarithm. What's that? Yeah, so I have plus because it's on the top, and then I have minus because it's the divided by 7 divided by. I mean, here's a more general. Well, just an example, really. AB over CD, if you had that pattern, that would be like log A plus log B minus log C minus log D, etc. This is how it works. Because you can apply the rule for 2 things to like 3 things by doing it twice. So like by repeated application of the rule for 2 products of 2 things or division of 2 objects, you get these extended laws. Now I can pull out the 5, right? Pull out that 5, and sorry, my 5 and my s look too much alike, but that's 5 log base 2 of s. Well, log base 2 of 7 is a number. I can't really, I'm just stuck with it. But I can pull the 2, right, yeah. So that's minus twice log base 2 of t. And that'd be my answer for that one. How about number 42? What can we do there? The cube, remember that's another notation for that is what? Log of x squared plus 4 to the 1/3 power, right? So by the power property, x to the log of x to the p is p log x. And, here the...
1/3 log x squared plus 4, right?
Yeah, 1/3 log of x squared plus 4.
That's it?
And that is it, because one thing I always try to tell people, log of a plus b is not equal to anything nice. There is no rule for breaking up the log of a sum. You gotta be careful. The log of a product becomes a sum of logs. The log of a quotient becomes a difference of logs. But if we have addition inside the argument of logarithms, nothing particularly nice happens typically. The only way something nice can happen is if you can somehow like factor something out and take that sum and convert it to a product. That's about it. All right, so move along here. I think it's healthy to work a harder problem on occasion. So here's one. Number 48. Here we have the log of the square root of x, of the square root of y, of the square root of z. Notice how they're nested. So I can pull the first square root out with a half, right? Got 1/2 log of x times the square root of y times the square root of z. And then I can leave the half out front, And I've got log of x plus, the log of the square root of y of the square root of z. Then I can pull half out of that, right? Because it's the square root of stuff. And I'm going to have log of y plus the log of the square root of z. If you'll forgive me if I skip a step there. Heaven will forgive me if I let out class early. I know my audience. What's that? Well, no, I've given Maggie false hope. So then the square root of z we can pull a half out of again, right? So we've got 1/2 of the log of x plus 1/2 of the log of y plus 1/2 of the log of z. Notice the fact that and then multiply that out, you got 1/2 log x plus 1/4 log y plus 1/8 log z. So that's one way to work this problem. Can you tell me another way to work this problem? Just not do it. Just not do it. Use a book calculator and do that. Use a calculator. It is true. If you put this into Wolfram Alpha, it would help you, right? Just like if you get a car, you can, just drive a marathon in no time. It doesn't help you run it though. So this is x times y, z to the 1/2 to the 1/2 to the 1/2, right? So by laws of exponents, this is x to the 1/2 times y, z to the 1/2 to the 1/2. Well, 1/2 times 1/2 is 1/4, which is x to the 1/2, y to the 1/4, z to the 1/8. So if you look at that expression and take the log of it, you immediately get, by properties of logs, 1/2 log x plus 1/4 log y plus 1/8 log z. Maybe that's an easier way to do this problem. I don't know. But again, you could use laws of exponents as another way to think here. Now problems 49 through 58 in section 4.4 are the other kind of direction of things, all right? And so let's look at some of those. So here we're supposed to combine the logarithms, all right? So like number 54. Here we've got log base 5 of x squared minus 1 minus the log base 5 of x minus 1. So we're supposed to combine and simplify. All right, that's one. Number 52 is maybe also worth looking at for a second here. Number 52 is 2. Oh, yeah. Okay, so 3 log 2 plus 2 log x minus 1/2 natural log of x plus 4. All right. So if we've got a minus, what does that do? We put it together, we get what? division, right? So we've got x squared minus 1 divided by x minus 1. Does that simplify? What's that? Yeah. What is that? That's log base 5. X plus 1 times x minus 1 upstairs, right? Divided by x minus 1. So the x minus 1's cancel. And we just got log base 5 of x plus 1. So you might say, do you mean to me we still need to know how to factor in this material? Yes, it's all true. The factoring never goes away. Yeah. How about this next one here? What do we do here? So we've got the natural log. I'm going to do it all at once. First of all, I've got a 2 to the power 3 from the first term, right? Times x to the what? You know what? Just try. Your secret is safe here. I will not tell anyone outside of this class that you've answered a math x squared, yes. I promise I won't tell other people. You know, I mean, well, at least, I know, but I don't, you know, that's what I should have. I should have like one video pointing at the board, and I should have like another one pointing back at the students. That would be split screen. I don't want that. Yeah, and then so minus 1/2 log of, now that one, so that's, well, I could write it this way, that would be times x plus 4 to the minus 1/2 power. I mean, I could write it that way. And I mean, but more to the point, that's the log of 8 times x cubed divided by the square root of x plus 4. All right, so there, I don't know, you know, there's about 50 problems like that in the book, right? And I would encourage you to, you know, work through a good swath of those until you really, really have internalized these rules and how they work, you know? Although I say that, but what's that? I mean, this is pretty much all I have to say about section 4.4, but now I'm going to go to section 4.5 and solve some equations. So we're not done. I told you it was a false hope. All right. So let's see if we can solve some equations. So they're probably, I don't know, about 5 or 6 different types of problems in section 4.5 to master. We'll start at the beginning. So here's section 4.5. I'll just try to work some representative problems from each subsection. Let's work number 6. Here we're faced with the problem 10 to the power 2x minus 3 equal to 1/10. So one way you could solve this problem would just be to go, oh, hey, that's 10 to the minus 1. All right? And there's a theorem if a to the x is equal to a to the y, that implies x equals to y. This is the so-called one-to-one property of the exponential. Right? And so, I mean, if you know about that, then once we have 10 to the 2x minus 3 equals 10 to the minus 1, then we can say, okay, so 2x minus 3 equals minus 1.
Wait. How can we say it was 1/10?
1/10 is 10 to the minus 1.
Wait, no, like, is this like, did we already know this? Like, I thought we only knew like 10x, or 10 to the
I see this is troubling you. So I'm using the theorem that there's a one-to-one property of, but, you know, fine. If you don't like this, it's okay.
I was just wondering, like, if this was like all, if this was written in the note back in the question, the question,
The question is to solve this equation. Like, this is the given problem,
Oh, well,
is to solve that.
so I was wondering if it was like only the 10 is 2x minus 3 power. I thought it was just that, no, 10, 1/10.
Huh.
I thought it was that.
Okay. I mean, I'm not
I
done.
didn't know it was anything, I didn't know we had information past the equal signs.
Yeah, this is an extra step by me, right there.
Not that one, the other one. I thought that one wasn't given to us.
Over here?
You know what, never mind.
I'm
Never mind, I got it.
oh, okay.
I was just saying the 1/10, I thought it was not given when they
You didn't know it was part of the problem.
Oh, no, that has to be part of the problem. This section 4.5 is equations. So it's like expression equals expression, solve for the variable. Section 4.4, it's like here's an expression involving logs, simplify it according to either like collecting or expanding. That's a summary. So here the answer should either be like a number or a couple numbers or no number at all, you know? So by the one-to-one property, I get that. And so that implies what? Yeah, 2x equals to 2, x equals to 1. Now, sometimes I don't like the one-to-one property, so I like to think about this a different way. What's another way you could solve this problem? How about this? Just take the original problem and take log base 10 of both sides. Or common log. Common log of 10 to the 2x minus 3 equals common log of 1/10, right? Of course, that's the common log of 10 to the minus 1, right? And so this is 2x minus 3, and this is minus 1. So again, we just get 2x minus 3 equals to minus 1. Like this theorem I'm telling you, the one-to-one property of the exponential, the proof of the theorem is just to take the log base a of both sides. Like if a to the x equals to a to the y, then log base a of a to the x equals to log base a of a to the y, which shows you x equals to y. This is the proof of that theorem. I don't do many proofs in here. This one I'm showing you because this is actually in the style of the calculation that we need to do. All right? But anyway, if you do have the same exponential on both sides, you can just equate the arguments. Got to be careful. It has to be exactly that. If there's a minus outside the exponential, it like messes it up. It's very fussy. It has to be exactly the format. A to the x equals a to the y. Like if it was a to the x equals minus a to the y, that would be totally different. Okay, move on here. Try to be more rapid fire in my exampling here. Number 8. Here we have e to the 1 minus 2x equals e to the 3x minus 5. So by the one-to-one property for the exponential, or you could take the natural log of both sides, we get 1 minus 2x equals 3x minus 5, which then tells me 6 is equal to 5x, x is equal to 6 over 5. So these don't have to be bad, right? Number 10 is a little bit more cranky. Here we've got 10 to the 2x squared minus 3 equals to 10 to the 9 minus x squared, right? So if we take the log base 10 of both sides, what does it give us? We get 2x squared minus 3 equal to 9 minus x squared. And what is that? I should bring all the x's to one side, right? Get, well, like 3x squared equal to what? 12, is it right? So x squared equals to 4. What are the solutions? Plus or minus 2. Hooray. Yes, x is equal to plus or minus the square root of 4, which is plus or minus 2. So this problem had 2 solutions, right? All right. Let's work some ones that are, so the problems 3 through 10, they're basically involving the same base. These are kind of like the most simple version of these problems. Now, like the problems 11 through 38, they're a little bit more advanced. So let's try to do some of these. Number 16. Here we have 3 to the 2x minus 1 equal to 5. So what I do here, I've got some, that's got base 3, that's a 5, right? So to me, when I see something like this, I just think, I'll take the natural log of it, because taking log base 3 doesn't really delight me much. So if I take the natural log of both sides of this equation, what do I get? By the power property of log, that's 2x minus 1 times the natural log of 3. And now I can solve for x. See, I get 2x log 3 equals the log of 3 plus the log of 5. And so x is equal to log 3 plus log 5 divided by 2 times log 3. And of course, we could plug it into our calculator and, get something more like a decimal form of the answer if you wanted, I could also rewrite this for what it's worth. That's the log of 15 over twice the log of 3. Or I could say log of 15 divided by log of 9. I don't know. I mean, there are various ways to rewrite the answer. And this doesn't really matter to you, but for me as a grader, I have to be careful, because a student could solve this a different way and have a really different looking answer. What's another way you could have solved this problem?
Power rule
power. How about if I take log base 3 of both sides, right? I mean, that's nice in the sense that I get 2x minus 1 equals to log base 3 of 5. So that gives me 2x is equal to 1 plus log base 3 of 5, which gives me that x is equal to 1 plus log base 3 of 5 over 2, you know? So is what I just wrote in magenta easier? Maybe. I don't know. To me, they're the same, but... Did I tell you guys to change the base formula? Nope. All right. Oh, you didn't say. You just said don't. Yeah, that's cracked me up. Okay, so log base b of x is equal to log base a of x divided by log base a of b. This is the change of base formula. So this right here, we could look at as 1/2, right? Natural log of 3 over natural log of 3, fine, plus the natural log of 5 over the natural log of 3. Of course, log 3 over 3 is 1, right? But natural log of 3 over the natural log of 5, well, see, in the case of the natural log, this looks like natural log of x over the natural log of b. All right? So, in fact, natural log of 5 over natural log of 3 is exactly log base 3 of 5. So, yeah, I mean, this answer and that answer, they look quite a bit different, but they're actually the same answer. So. Let's work another. Number 32. Here we've got 125 to the x power plus 5 to the 3x plus 1 equal to 200. Interesting. Number 38 is 10 over 1 plus e to the minus x equals to 2. So we'll also work that one. So, see, this one's annoying. Number 32 is annoying because, you know, before we've been able to isolate the exponential, right? But here we have a sum of exponentials. And remember that the log of a sum is nothing nice, right? So in order to be successful here, we have to find a way to, like, combine those terms. Can you tell me how? Oh, how about this? 125 is what? 5 cubed, right? So what we're looking at is really 5 cubed to the x power plus, well, the second term is actually 5 times 5 to the 3x power, isn't it? So what we're really looking at is 5 to the 3x plus 5 times 5 to the 3x. In other words, what we really have is 6 times 5 to the 3x equals to 200. Or we could divide the 6 to the other side, right? So we've got 5 to the 3x is equal to 200 over 6. And now